Good morning, Astronomy 1020. Welcome to another exciting lecture and homework session. Today is lecture number 6. We are going to actually start talking about our first astronomical object, the sun. And we're going to do a homework on the sun. Now, I am roughly half a lecture behind. So today is going to be a little frenetic because the homework questions that we're going to solve today are complex and cover a lot of different areas of the sun. But because I only have 1 hour and a half segment to work with, I'm not going to be able to cover all of that. So I'm not sure how this is going to work. I think our lecture for the sun is going to cover today. It's going to drift into next Tuesday, maybe even next Thursday. Also, keep in mind, everyone, that we have an exam coming up, not next week, but the Tuesday after that. So at some point, we'll want to talk about that. And the best way to prepare yourself for that is to engage in the homeworks. And when we're doing sample problems, make sure you're punching into your calculator and trying to get the same numbers as us. I cannot stress how important it is that you guys in your home office there or whatever are punching along with me. So let's get to it. Let me talk to you guys. I want to start off by kind of trying to get you guys excited about why the sun is interesting and beautiful to look at, why we should care about it. Up to now, you guys have been in a sort of baby physics training academy where you learned about gravity and you learned about light. You learned about basics of counting big numbers and looking at the rotation of the sky. Now it's time to put all those tools together and actually use them to analyze our first astronomical object. The sun is our closest star. It's the star that we know the best and have the most data and imaging available from. So it seems like a pretty good place to start our journey of learning about stars. I'd like to talk to you about where a lot of the images and videos that you're going to see come from. There's a satellite that's operated by the Smithsonian Astrophysical Observatory. It's called the Solar Dynamics Observatory. You can actually just type SDO into Google and you'll get it. So the idea behind the Solar Dynamics Observatory is it's kind of like a satellite / telescope that orbits Earth, but its job is to continuously point towards the sun and continuously image the sun at a variety of different wavelengths across the electromagnetic spectrum. So obviously they're imaging it in visible light, but they're also imaging the sun in infrared rays, in ultraviolet, and even in X-rays. And as you'll learn in our journey today, when you image the sun at different wavelengths of the electromagnetic spectrum, you can see into different layers of the sun and understand different parts of the physics at work there. I'll also mention that their website is really cool because they're perpetually updating it with live images of the sun. You'll notice that this image was taken today, October 8th, at 15 hours Universal Time. If we subtract 5 hours to get to Eastern Standard Time, that was taken at 10 a.m., so an hour and a half ago. And this is the sun at 171 angstroms or 17 nanometers. Today, the sun is magnetically quiet. It's at a solar magnetic minimum. So the sun is pretty chill, and it's not going through too much active magnetic eruptions. But I'll show you some videos today that demonstrate that the sun can actually get quite violent and turbulent at its surface. And those videos are a lot of fun to look at. So you can also go to the data section on this website and you can browse their daily movies. And that's a lot of fun because you can just kind of click on any date, any year. I don't know, Christopher Leonard, what's your birthday?
1998.
No, your month and year. I'm sorry, month and day.
Oh, January 22nd.
So last year, this is what the sun was doing on your birthday. You can just go and click any one of these images. I think these are usually pretty cool. And this is what was up with the sun on your birthday. This is a movie that's probably several hours of observations sort of compressed into about a minute. and you can see the sun rotating here. This is roughly at X-ray wavelengths. So let's not get ahead of myself here. Let's start by looking at a typical day on the sun from the Solar Dynamics Observatory. And I'm starting off here at visible wavelengths. This is 4,500 angstroms or 450 nanometers. Now, these discussions are going to get cooler and more intense if you guys know some things. So let's see what you know. Can any of you tell me what color 450 nanometers is on the electromagnetic spectrum?
Is it purple?
Yeah, kind of. Very good. But Austin, I think there's a better name for this color. Let's find a picture of the visible spectrum here. Sorry. I'm trying to do this from memory. Is it purple or is it?
It's blue.
Oh, come on. We can be more imaginative in our color terms here.
Azul?
450 nanometers is not merely blue, Sarah.
Indigo.
Is it indigo?
It's indigo. That's right. Yes, thank you. So that's cool. You guys know some stuff. I'm impressed. But here's the issue, right? Why does the sun look yellow in this picture when they are taking it with a filter that only allows indigo light through? Why do you think the sun looks yellow? Okay. It's not the angle. All right, the
The
answer's
temperature.
no, the answer's kind of lame. It's because they fake colored it that way. They just colored it yellow to make you feel good. Why did they do that? They did that because if they showed you an image of the sun that was indigo, people who don't, you have been deceived. If they showed you an image of the sun that was indigo, if you were a random person that was not informed about the electromagnetic spectrum, you would be mightily confused that you were supposed to be looking at the sun at visible wavelengths. The sun might look yellow from the ground, but what color do you think the sun is from outer space? Maybe that could be something.
Isn't it white?
Yeah, it's the purest, whitest white you've ever seen. Of course, they could have also colored it white, but then people would feel like they only had a black and white image and they wouldn't get their money's worth or something. So they fake colored it to make you feel good, but this is probably what the sun would look like at yellow wavelengths as well. For some reason, their filter was in indigo. I don't know what the purpose of that was. Now, this is a movie, okay? And what I'm going to do is I'm going to hit play on the movie, and I want you to just kind of watch what happens. There'll probably be a little lag because this is a very high resolution image. As the movie plays, you'll notice the sun is rotating. The only reason you can even see that it's rotating is because you're tracking these things over here. Do you guys know what these little spots are? They're called sunspots. They're an important part of the physics of the sun. And the moral of the story that you're seeing here is that the sun at visible wavelengths is actually pretty boring. When you look at the sun at visible wavelengths, you are seeing a very particular layer of the sun, a layer that I will call the photosphere. The photosphere is sort of like the surface of the sun, but it's not a surface in any physical sense like the hard ground that you're standing on. It's made of gas. But this gas is important because it's the layer that produces visible light. So when you look at the sun on the sky, this is the layer that your eyeballs are seeing. Sunspots are an important part of tracking the rotation of the sun. Now, it doesn't look like the sun is rotating very quickly, but you need to remember that the diameter of the sun, okay, this line here is 1.4 million kilometers across. That's kind of huge, right? The sun is actually rotating quite rapidly, but because it's such a massive sphere, it doesn't look like it's doing very much. These sunspots, I wonder how big they are. Maybe we could do a little quick exercise. I kind of don't have time for this, but I think this would be good for you guys anyways. Let's do a quick exercise on the size of sunspots because it's fun and it'll get you to use your calculators this morning. So we know that the true diameter of the sun across is 1.4 million kilometers. And the thing that we'd like to start thinking about, just to get a scale size of the sun, is how big is a sunspot? Guys, okay. So the question we want to ask is, how big is that spot? Anyways, what I'm going to do is I'm going to take out a ruler and I'm going to measure the size of the sunspot, and I'm going to measure the size of the sun. And I'll give you those values in centimeters, okay? So here I go. I'm going to share screen. I'm going to look at that sun. Now, guys, write these numbers down for me. When I measure the diameter of the sun, 12.6 centimeters, okay? And the size of the sunspot is 4 millimeters. Okay. So this is 12.6 centimeters. This guy is maybe 4 millimeters. Students, tell me what to do. If I want to know how big that spot is in kilometers, how would I go about this? This is a skill that you were trained to do in your first set of lectures.
Convert it to kilometers.
Good. Okay, Christopher, you're up. What should I do? Actually, I should call him Blair is what I should do. But no, okay, Christopher, talk to me here.
Okay, you need to do the whole
Dimensional analysis. What should I start with?
Start with the 4 millimeters.
Fine. Then what do I do?
X with the line.
Yep. So far, I like everything that you're doing.
I forget how many millimeters are in a meter, so I'm just gonna go centimeters.
You don't have to go to meters. You
Meters
remember
on
that when
bottom,
we are creating a
top.
scale factor. We're creating a scale factor in which 1.4 million kilometers is equal to 12.6 fake centimeters. So I was going to see if you guys could do this on your own, but maybe that was too much for you. You know, when you make a scale model, when you have to convert a scale model, you first have to come up with a scale factor. You have to say this many kilometers is equivalent to this many centimeters on the screen. Does that help? Feel free to chime in and help Christopher, guys, because he's trying to do this all by himself here, while the rest of you are just, you know, micromanaging or middle managing, whatever you call it. I think I've had too much coffee for you guys. Yes, you can, Cameron. You can do it. Come on, Christopher. Oh, I see, Cam. No one? Come on, a run sack, you know what to do.
I'm trying to Google it. Can you hear me?
No, you don't Google it, guys. You used to mention this.
I'm Googling the conversion factor.
No, you don't have to.
No, is that cheating?
Yes, it is,
Dang.
because everything you need is right here. You can't Google this because Google doesn't know how big the sun was on my screen. What units would you like to get to at the end?
Centimeters.
False.
Kilometers.
Yes. What's stopping you from getting to kilometers right now? Oh, I don't have time for you guys to be slow today. I do not have time for this. Okay, look.
Is it centimeters? We need to convert to centimeters and then to kilometers?
Yes, Wyatt. All right, Wyatt understands. Wyatt, walk us through that. Yes, Cameron.
All right.
Cameron, okay, we're giving you love, but you're a troll. Okay, so come on, Wyatt, tell me what to do.
Millimeters on the top and centimeters on the bottom.
Wait, that don't make no fucking sense. You got to cancel out millimeters.
Oh, yeah. Okay, never mind. The other way around.
Okay, fine.
Yeah.
All right, so first Wyatt recognizes that if he's going to utilize that conversion factor, he's got to get this out of millimeters and into centimeters. What's the conversion factor for that?
Mil is 1,000, right? And then cent is 10. So Would it be 100?
I need to focus. Dude,
Mm.
let's just break it down here. I wish I could record scratch. This is a centimeter. The little tick marks are millimeters. How many millimeters are in a centimeter?
10.
Thank you. All right, so give me my conversion factor.
10 on the bottom,
That's
and then
right.
1 on the top.
Okay, what do I do next, Wyatt? Keep going.
We're gonna do the X bar again,
Yep.
and then we're gonna do we need to multiply that by. Okay, we're trying to get kilometers, right? So we do that on the bottom.
Wait, what is that on the bottom? Be specific.
Kilometers. We would put kilometers.
Does that cancel out centimeters? No, it doesn't. That's bad dimensional analysis.
We got to multiply again because we're getting there. So yeah, kilometers on the top and then centimeters on the bottom.
Guys, if you still haven't mastered dimensional analysis, whatever's up here always needs to go down there. That's the only way this works, right?
Okay.
And then what's on the top?
This way we're gonna do on the top 1.4 times 10 to the 6th.
Yep. And on the bottom?
12.6.
All right. Now I'd like you guys to punch it up, but y'all so slow, I ain't got time for that today. So let me do it for you. I'm going to do 4 times, I'm going to do 4 divided by 10 times 1.4 million divided by 12.6. And I get 44,000 kilometers. That's the size of that little sunspot. But maybe you ought to think about what that means. Do you guys know what the radius of Earth is? What's the radius of Earth? No, it's 6,400 kilometers is the radius of Earth. What's the diameter of Earth?
$128,000 kilometers.
12,800 kilometers, right?
Yeah.
That's the diameter of Earth.
Oh yeah.
What's my point, Wyatt?
What's my point? Are big.
Yeah, let's be quantitative instead of qualitative.
All right, they're almost, so that sunspot's almost 4 times the diameter of Earth.
Exactly. That sunspot is 4 times bigger than Earth. Do you see? Now, I could have told you that, but that's not fun. It's fun when you know how to do it yourself. Think about that, Wyatt. Let's look at this video again. It looks like the sun is rotating slowly, but every hour, that thing is like pushing 4 Earths across. This thing is zooming. That sunspot is 4 times the size of Earth. Try to think about how big the sun is. It's a stupid big ball. Okay, now listen. There's another point here. What if I were to show you the exact same day, the exact same window of time, but instead of showing it to you in visible light, I were to switch my wavelength of observation and go to X-rays? What would the sun look like? Well, here is that exact same day, exact same window of time, but now we're watching it at 17 nanometers, which is right on the cusp between ultraviolet and X-rays. Watch that same window of time. The sun is wild. You see all these crazy magnetic fields poking out. Look at these prominences, these vertical sheets of plasma, these powerful magnetic fields. In a few seconds, somewhere over where my cursor is, you'll see a massive eruption of plasma that's called a solar flare. Watch this thing. So the magnetic activity builds up, and then boom, you see this huge eruption of gas. Considering that that sunspot was 4 times the size of Earth, can you imagine how big that jet of plasma was that just got blasted off the sun? The sun is dynamic and wild, but you have to look, yeah, like a big nuke in some ways. In fact, it's even cooler than that, Arunsak. Let's look at a couple of different zoom ins. So suppose we tune our wavelength and we zoom in using the Solar Dynamics Observatory. Now this video is a little cheesy. It's got space music, which I am into. Let's get out of this stuff. And let's watch what happens on a typical day in the sun. First, you can see the magnetic fields are building up energy and they're poking off the surface of the sun. And as the magnetic field pushes out of the surface of the sun, it's pushing hot gas and plasma with it. But the plasma is constrained to move along magnetic fields. And what you see is a giant plasma waterfall that's maybe 8 Earths tall. And all of that hot gas is dripping down the magnetic field lines onto the sun. The sun is wild. It's violent, it's dynamic, it's interesting. Sometimes these magnetic fields build up so much energy that, yeah, Runsack, they can kind of act like big nuclear explosions, but it's not a nuke. Okay, this is not these explosions are not nuclear. The nuke is happening in the interior of the sun, a Runsack. Watch this. This is something called a coronal mass ejection, and I want you guys to see this video. It's like 5 seconds long. Boof! Look at that. That eruption of gas was half the radius or half the diameter of the sun. It was the sun's radius. Okay, thanks, Runsack, for keeping it classy. Okay, we want to understand what's going on there because it's cool. It's interesting. These are things that are worth talking about. So let's learn a little bit about the sun, shall we? All right. The sun. When you start learning about the sun, you kind of have to know. Oh, by the way, for anyone who actually reads the book, which is probably no one anymore, because you're all Gen Z kids, almost anyways. The sun is in chapter 14. If you want to look and follow along with these lectures with the reading, that could be very helpful. The two things that we want to know about the sun are its composition and some physical dimensions or properties. So let's put those on either side of a table here. There's some helpful facts to know. And one are the physical dimensions. The other is the composition. Let's start with the composition, or let's do the physical dimensions. There are 4 numbers that parameterize any star. The mass, which you guys know is 2 times 10 to the 30 kilograms. The luminosity of the sun, 4 times 10 to the 26 watts. The radius of the sun, 700,000 kilometers. And the temperature at the surface of the sun, the temperature of the photosphere, which I'm going to call T subscript phot, is 5,800 Kelvin. The nice thing about these numbers is these numbers do not change very much over a star's lifetime. For most stars, they maintain a fixed mass, a fixed luminosity. The radius is a little wiggy, but we'll get to that later, and the temperature at the surface of the star. Therefore, if you know these numbers, they kind of tell you the physics of the star, and they're kind of a good place to start when you're just trying to think about what the hell is the sun anyways. Its composition can be broken down by mass to be 70% hydrogen gas, 28% helium gas, and the remaining 2% of the sun, I'm going to use a charged term in astronomy, a term that means something special to astronomers. They call it metals. But what metals is code for in astronomy? Metals just mean heavy elements. And heavy elements could be anything on the periodic table that is more massive than hydrogen or helium. Yeah, there's some gold in there, Cameron, but there's also things like carbon, nitrogen, oxygen, silicon, iron. Okay, fine. Gold. Wait, what is it? Is gold AU? In the case of our sun, not so much, Wyatt. We'll learn about that. Guys, we should just take a quick kids break and talk for a second about the periodic table of the elements for a second. So let me go to my lecture on radiation, and somewhere around here, I've got a periodic table. Okay. So just a quick show of hands. How many of you have had chemistry at some point in your life? I just want to know what the level I'm talking to here is. So Wyatt, Emily, Runsack, Christopher, but not everyone, okay? So I'm not asking if you're good or if you remember everything, just have you had any chemistry at all? So here's how this works, guys. When you took a chemistry class, your chemistry teacher taught you that some elements were considered metals and other elements were non-metals or insulators or something like that. And the dividing line is usually somewhere about here on the periodic table. So there are things that you think of as metals without too much trouble. When you think of a metal, you might think of copper or cobalt or nickel or iron. These are the kind of things that come to mind when you think gold, silver. You may not think about beryllium or sodium as metals, but they are a type of metal because what makes a metal is that it likes to give up electrons. On the other hand, things that are insulators or nonmetals, they tend to be things like carbon, nitrogen, oxygen. That's fine if you're a chemist and you're just working with the materials you have on Earth and you're trying to separate every single atom. But let's think about this from an astronomer's point of view. The sun has a composition which is 98% this, hydrogen, and helium. All right, so it's 70 plus 28. So 98% of the sun is hydrogen gas and helium gas. And it's going to turn out that when you look around space, most nebulas in outer space also have this composition. So for an astronomer, these two elements are pretty much like the whole universe. And all of this other stuff below it is like little teeny bits of scrap that are left over. They're little tiny bits of grit. So astronomers just, they have a joke or a nickname. Anything that is not hydrogen or helium, it's a heavy element or it's a metal, okay? But keep in mind, astronomers use the term metal in a different way than chemists do. Metals just mean heavy gick. 2% of the sun's mass being metals might not sound like a lot. But what if I asked, all right, first of all, does everyone have these notes? Because I need to erase.
No, one more second.
No comment. Do you guys have these notes? All right. I want to ask you guys to solve a little question related to our homework today. And it's another thinking question, a very simple one. What is the mass of the 2% metals in the sun? Has anyone had enough coffee to do that problem? Let's ask our resident banking friends, Austin and Caitlin, to help us with that. As bankers, you guys should be very good at percentages. Since you're
Well, I got fired today because my branch closed, so I guess Caitlin, it's up to you.
Oh no, Austin.
My computer does all the work for me. You're asking the wrong person.
Yeah, but at some point you gotta, haven't you seen Terminator? We're gonna have to fight these machines someday. It's gonna be up to, well, you're missing out.
Oh.
Get someone to watch Terminator with you.
Early.
Okay, listen, you guys can handle a percentage, I'm sure. How do I do this problem?
Make the bar.
Okay, yeah, Wyatt's got the answer, although he doesn't have units, so I don't believe it. Make the bar, but what else? Okay, all right, so I'll make the bar.
Well, actually, don't make the bar.
I don't need to make the bar.
Mm-hmm.
It's not about the bar. Just keep it simple.
Just multiply by 0.2.
Multiply
Well,
what?
0.0. The mass, which is 2 times 10 to the 30 kilograms.
Exactly. That's all we got to do. 2 times 10 to the 30. You can do this without a calculator too. What's 2 times 2? 2 times 2 is 4. What's the power of 10 there?
Negative
10
2.
to the negative 2. What's 30 minus 2?
28. There's better interest than we'll get, and then you check the process.
This is the mass of the 2% metals. How does that compare to the mass of Earth? The mass of Earth is 6 times 10 to the 24 kilograms. What's the ratio? Well, come on, someone punch this up for me. Wait, really? Is there a glitch here? No, Wyatt. 4 times 10 to the 28 over 6 times 10 to the 24 is not that number. You should all be punching right now. I already know what the answer is. I know all this stuff. I can't download the information to your brain. You have to learn it one piece at a time. Well, I'm taking a break.
6,000 times.
Isn't it closer to round better?
7,000 times.
All right, yeah. It's like 7,000 times. And what's the meaning of the 7,000? 7,000 times what?
Bigger than the sun. I mean, bigger than the Earth.
Do you mean bigger as in size, or do you mean big means size? What were we measuring there? Oh, you don't understand, do you? It's
More
it's,
massive.
Thank you, Christopher. It's more mass. Look, guys, if you think about it, this is what the solar system is. If you could extract just 2% of the sun's matter, if you could just extract all of those metals from the sun, you could crush that down into another 7,000 planets. When I think about the solar system, I think of the sun. The solar system is the sun. And all of these guys, all of these planets, it's the 2% grit, the 2% metals that didn't fall into the sun because they were rotating too rapidly. Planets are made from the little grit and the little bits of metals that are not part of the sun's mass. But most of the sun is just made of pure hydrogen and helium gas. It's a big ball of gas. Or is it a ball of plasma? What's the difference between those two things? Y'all know?
Plasma is like superheated gas.
And what happens to the gas when you superheat it, Christopher? Yes, you are correct. So you superheat the gas until something happens. It's changing its state. The sun is a ball of neutral gas and plasma. It's kind of got both aspects of it. Let's just start by talking about hydrogen. What is the composition of your most common isotope of hydrogen, protium? That's going to be a test question. No kidding. What's the composition of a hydrogen atom? If you guys don't know what hydrogen is, then we're screwed. Then I can't even take one little tiptoe through the cosmos with you. You need to know what hydrogen is.
1 proton and 1 neutron, or the electron.
1 proton, 1 electron is the most common isotope. So let's draw a little cartoon of what a neutral gas is like. In a neutral gas, the electrons are bound to the protons. So each of the atoms is, technically speaking, electrically neutral. And they float around in the soup and they bop into each other. They obey something called the ideal gas law, which I need to train you on. Actually, plasmas kind of obey the ideal gas law too, but they're way more complicated. Christopher, what happens when you superheat your hydrogen gas is the electrons begin to jump from lower orbits up to higher orbits and higher orbits. And if you keep pumping energy into them, they collide and smash into each other. And they eventually knock the electrons right off of the atom. They ionize the atom. But the thing they don't tell you in chemistry is the electrons don't disappear from the universe. They're still right there floating around with the protons. You have now created yourself a plasma. A plasma is a charged gas. So what you have is a sea of protons. And the protons have extremely high kinetic energies. So they're flying around, they're bopping around with each other. But you also have electrons with very high kinetic energies. And these electrons are also flying around. And what you have is a mosh pit of positive and negative charges. The thing that makes this different than a normal gas is in a neutral gas, here we'd better look at a cartoon for help. I think slide 22 has my ideal gas. In a neutral gas, if these pellets are hydrogen and helium, the neutral gas particles do not have any net charge, so they kind of just act like ping pong balls in a box. They act just like any pool table logic would work, where the little spheres just travel in a straight line until they smash into their neighbor and then they bounce off them. There's nothing that controls their motion except for collisions and straight line motion. But as I'm sure you could imagine, and it's difficult to get an animation for this, but once you add the charges, the particles are going to start swimming around and moving around in very complicated ways. For instance, anytime 2 electrons come close to each other, those electrons are going to behave just like the way magnets behave when you try to push 2 north poles together. You know how when you try to like force 2 magnets together, you kind of bring them together and they kind of push off to the side, like you can see happening here. Anytime 2 protons or 2 electrons come near each other, they'll feel an electrostatic repulsion, which will go whoosh and push them off to the side from one another. So the particles are like swimming around. The electrons and the protons are trying to get together, but they pass through one another because their energies are too high. But meanwhile, they're swerving. So they're doing this complicated bee dance. In fact, what really happens in plasmas is the electrons and the protons tend to separate, and they keep trying to come together like in some kind of a country line dance, but they pass through each other, and plasmas actually oscillate and ring like a bell. Plasmas are insanely complex, guys. You have to take a very advanced physics course. But I need to tell you about plasmas because that's what's going on in the sun. I want to show you guys one of my favorite YouTube channels. It's 10 years of observations, or it's several years of observations of the Solar Dynamics Observatory. And what they've done here is they've condensed it down to the Solar Dynamics Observatory's greatest hits. And if you go to this YouTube page, it's called Thermonuclear Art. It's especially cool if you have a high definition television or projector or something. So here you can see that they're going to be showing you different wavelengths from X-rays to visible. And, you know, they have to work hours and hours just to create a minute of this footage. But this video here, they've got some nice relaxing space music. Sometimes I put this on in my projector at home and I just eat a tomato sandwich and I just stare at the high resolution video of the sun. It's kind of a fun thing to do. But you can see the surface of the sun has a mixture of gas and plasma that's interacting in complicated ways. And if you see all those crazy lines poking out of the sun, those are all magnetic field lines which are being generated by the motion of plasma particles. If you look really close in this video, it's probably reduced the bit rate a bit because we're watching this over the internet, but you can actually see plasma waves radiating across the surface of the sun. You can see that plasma gas interacting with itself in complicated ways. And it's really beautiful. So all of this cool magnetic activity that you see on the sun is related to the fact that the sun is a mixture of neutral gas and plasma. In the They Might Be Giants song, I can't remember what the name of the song is, but they have this line that goes, "The sun is a mass of incandescent gas." And that's not a bad thing to say. Plasma is a gas and neutral gas is gas. But plasma kicks things up a notch. It adds magnetic and electric activity. If you could think about the sun as a giant sphere, here we go. The sun is a ball which starts off hot at the surface. In fact, close to 6,000 Kelvin hot. But as you go down layer by layer towards the core of the sun, it gets insanely hot. In fact, it's going to turn out that the core temperature of the sun, which is a number I kind of want you to memorize, the internal temperature of the sun at its core is a whopping 15 million Kelvin hot. And that is hot enough for hydrogen fusion to occur. We need to learn about hydrogen fusion today, this week, so that you can understand how the sun generates its energy. Because it starts off hot and it gets even hotter, it means the mixture of gas to plasma changes from the surface of the sun to the core of the sun. And I'm just going to say something simple and easy to understand. Here at the surface, it might be, oh, I don't know the exact percentages, but I know there's something like this. It might be like 98% gas and maybe 2% plasma. These numbers are a little loose. So I don't remember the exact ratios, but I know at the surface of the sun, there is much more gas than plasma. By the time you get into the core of the sun.
Professor?
Yes.
The board's mad blurry. And everyone's having the same. The board is blurry. Everyone's having.
Everyone show your hands if the board is blurry for you.
Oh, that's in class. No, isn't this counseling?
Oh. Wait, I don't get it.
It might be your Wi-Fi. It's either you're like going from yellow bars to full bars.
Okay, you know what it is? Maybe it's because I'm right. You know what? I see what's going on. That video of the Solar Dynamics Observatory, it's so high resolution that it was probably competing with my bandwidth. That's what was going on. It's my horoscope. No, sir. Okay, tell me now, class, does it look better now?
Better, but it's still pixelated.
See, it doesn't look pixelated on my end. Let me cut down.
Oh, there you go. I'm good now.
Okay, so I think this is actually interesting. Every tab that I have open was hurting your bandwidth. So that's a lesson for me to keep my tabs closed. Tech support, 10 out of 10. Okay, so you guys can see it clear now, correct? All right, let me explain that point one more time. Now that you can see what's going on, at the surface of the star, it's mostly gas with a small amount of plasma. But as you get in towards the core of the sun, at these temperatures, the sun is like 100% plasma. So if you say the sun is a ball of plasma, you're not wrong because most of the interior is plasma. If you say the sun is a ball of gas, that's also not wrong because gas and plasma are both gases, right? But there's a nuance here that I'm trying to help you understand. The mixture, the change between gas and plasma, it affects the way the sun behaves.
At what temperature does the gas start to become a plasma?
That's a really good question. I knew this at one point. It's somewhere above 10,000 Kelvin. I think 9,000 or 10,000 Kelvin. That's a really good question, Wyatt. That is a deeply meaningful question for this class. So we'll have to look that up. It depends upon. Oh yeah.
Well, I was just saying, I was curious because I know that like the surface of the sun is 5,800 Kelvin, but the corona is so much more hot than the surface. So I'm curious, can plasma appear in the corona of the sun?
Yes. Okay. So Wyatt's actually addressing something that I wanted to address. The sun is hot at the surface, but the surface is what I refer to as the photosphere. Wyatt, who knows some things, is correctly pointing out that the sun also gets a bit hotter up towards its outer layers. So it turns out, Wyatt, that the corona, which is up here, is entirely plasma as well. So it's also 100% plasma. The question that you asked, I realized, I can't believe it took me a minute to realize this. You can't answer the question the way you asked it, Wyatt, because you're assuming that pressure does not have anything to do with this. But the temperature at which something becomes plasma depends not only on temperature, but also on the pressure of the gas. And maybe that's a cool segue for us to talk about the ideal gas law. And then we'll get back to some of those questions.
Okay.
I'm erasing this cartoon. I don't even have time to wait. Okay, you need to know a little something about the ideal gas law and pressure. The ideal gas law is a relationship between temperature and pressure. And basically the ideal gas law is a mathematical formula that is trying to tell you this. It's trying to tell you what slide 22 is showing you. It's trying to have you imagine a box full of gaseous particles. They're traveling around and they're smashing into each other in a big mosh pit. If you ever took chemistry class, as a few of you have, you would have learned the ideal gas law as PV equals nRT. That's a lame formula. That's for weak sauce chemists, okay? Physicists, astronomers use a different variation of the ideal gas law. Pressure equals nKT, where P is the pressure of the gas measured in a unit called pascals. N is the so-called number density of the gas measured in some kind of kooky units, particles per cubic meter. K is a constant of nature known as the Boltzmann constant. And K basically shows up anytime you deal with gases in physics. 1.4 times 10 to the minus 23 joules per Kelvin is the so-called Boltzmann constant. And lastly, T is the temperature of the gas measured in units of Kelvin. Up to now, students, the only one of these parameters that we've talked about in depth is the temperature T. I should probably walk you through these other ones carefully. This isn't a varying parameter. This is a constant of nature. All right, but first, students, you have to earn it. You have to prove to me before I tell you what this and this is that you remember what I've told you already. So someone out there in my TV audience, tell me what the hell temperature is. If you can't remember what temperature is, I can't tell you what pressure and number density are. So
Would temperature be, and I'm not looking at any notes,
yeah, try to use the force.
use a force?
I meant like Star Wars, like use the force, Luke.
Oh,
Switch off
okay.
your computer. Trust your instincts.
Okay, it would be essentially like how much energy is in a particle or in like something, like how fast the molecules are moving.
Yeah, okay. Okay, it's a measure of the energy of the gas. It is a measure kind of how fast they're moving. That's pretty good, Austin. Austin did a solid job. Can anyone even improve upon that? Maybe now we'll switch on the computer and we'll see what the definition is in our notes. As in, someone go find it in your notes. Do you even know where that is? Where
I
did
have it. I'm
Okay.
sorry.
Sure,
It's a
Stacy.
measure of the average kinetic energy in the system of particles.
That's right. So temperature is a measurement of the kinetic energy of the particles. Although oftentimes I ask students to think of it as a useful lie, the particles usually have a single mass if it's a single species. So Austin's not wrong when he says the speed of the particles. In fact, since kinetic energy is a bit more abstract for you guys, the speed of the particles is probably a better way to think about it. All right. Let's talk about number density and pressure real quick. Number density means the number of particles in a box. And the box could be as big as a cubic meter, or oftentimes what we like to do is measure it in cubic centimeters. I had a little mini dice around here that I want to show you guys. I remember that I knocked it off this thing a couple of days ago. Well, I guess it's not the most important thing. The number density is different than normal density in that you're not doing mass per unit volume, you're doing number of particles per unit volume. So typically you define your unit volume to be either a cubic meter, or oftentimes we use cubic centimeters, and then you just count how many gas particles are in that box. Let's pretend a cubic meter is kind of big, so I'm going to work with a cubic centimeter. So let's say this is 1 centimeter cubic, and I've got 1, 2, 3, 4, 5 particles in my box. That would mean I have 5 particles or 5 atoms per cubic centimeter. Pretty straightforward, basic concept. A cubic centimeter is about the size of a chicken bouillon cube, or about the size of a slightly smaller than average dice, which I had as a kind of lame-ass demo, but I can't find it right now, so whatever. Okay, here's the thing that you need to know about number density. Cubic centimeters are a physically measurable unit, but particles are a conceptual unit. So one thing that I found very confusing when I was a student is oftentimes people write number densities with these units. they write number density as 5 per centimeters. Where you think inside of your head, I'm talking particles per cubic centimeter, but you don't always write the term particles. You just write 5 1/centimeter cubed. Sometimes when astronomers are feeling lazy or they just want to confuse their students, they'll even write number densities in this way. 5 centimeters to the -3. And that's the kind of thing that'll just give Astronomy 101 students the willies, okay? From now on, if you see me or anyone else write 5 centimeters to the -3, you're going to take a deep, calm breath and you're going to say, I know what that means. That means particles per cubic centimeter. This is something easy to think about. That's something weird, okay? Do you understand? I just want to forewarn you about that because it's going to happen before this class is over. Okay, number density is a simple concept. Let's tackle pressure next. Does anyone know what pressure is? If temperature is the speed of the particles, then what's pressure?
The amount?
No, number density measures the amount because that tells you how many particles are packed in the box.
Acceleration or the force?
It's like the force, but technically speaking, Austin, pressure is a force per unit area, okay? Now, when you say what is the force and what is the area, usually you imagine a bunch of gas particles in a balloon or something, and you imagine that there's a wall. This wall could be the rubber membrane of the balloon, or it could be the box that the gas is contained in. And the particles are traveling and smashing into the gas. I'm sorry, the gas particles are smashing into the wall, and as they hit the wall, they impart a force. So the force is the force of the particles smashing into the wall, and the area is like the area of the wall that the particles are smashing into. In the Mks system of units, we measure forces in newtons and we measure area in square meters. And we define this as 1 Pascal. 1 Pascal is defined as 1 Newton per meter squared. There are other units of pressure that I think you should know about. Do you guys know what the imperial units of pressure are? What if you go fill up your tires at the gas station? What units, or you pump air into your bicycle?
Pounds per square inch.
Right. Sometimes people write it as PSI, but it's pounds per inches squared. There's a couple others that I would like to tell you about. They are the bar and they are the atmosphere. People sometimes use these interchangeably because they're almost the exact same. Planetary scientists like to work in atmospheres where the Earth's pressure at sea level is the reference. Meteorologists like to work in bars. But the truth is that 1 atmosphere is roughly equal to 1 bar. And they are both equal to the pressure at sea level, like here in Rhode Island. The pressure is 100,000 pascals. Just for funsies, 14.7 pounds per square inch. So the pressure of gas, that's the air in which you're breathing right now, is pretty much 1 kilopascal. That's what they call it. They call it 1 kilopascal. I have an image somewhere. Maybe I can look here. Tire pressure label. Sometimes you can just find a nice picture. You know, tires, whether they're the tires, Here's a bicycle tire. Car. I want to see if we can find like a picture of a car, of a tire that has a pressure label on it. I have a picture somewhere. Here's a bicycle one. Oh shoot, that picture is small. I have one in my list of images, but I have images scattered everywhere. Tire pressure car. I just want to look at an up close picture of a car tire with you so that you can see that here we go, something like this. Okay. So what does this say, guys? Let's look up close. Here's another one. This is a high resolution one. Do they have this in, yeah, they have it in kilopascals. So what's the pressure? You can see it over here. How many times greater is the pressure in this tire than the air in the room you're sitting in now? Oh, 80 PSI is typical for bikes too, actually. Okay, so yeah, Cameron already knew that. I just didn't see his chat. So how many times greater than air pressure is this? Not 550 times, that's 550 kilopascals. Oh, I see. Did anyone notice that I screwed up here? That's not your fault. That's my fault. Well, it's both of our faults. Does that change your answer? You guys see what I did there, right? I made a dumb. All right, I did a dumb. Sorry. So not 550 times, but 5.5, right? Yeah, thanks, Arunsak. Okay, that was my bad, buddy. The state of matter, whether it's solid, liquid, or gas, depends both on temperature and pressure. And this is one of the reasons why, Wyatt, the gas in the outer envelope of the sun is high temperature, but it's also very low pressure, and it's completely in a plasma state. Okay, I want to move on from this. I want to see if I can do like 2 more things here before I run out of time. I need to talk to you guys about a concept that is very important in stellar physics. The concept has to do with why the sun should keep a fixed radius at all. The sun is like a ball of gas, right? And you can see the sun on your sky, as this picture dramatically demonstrates. Was that 17? Yeah. Now, this thing that he's holding in his hands is the sun, which you can resolve with your naked eye. And the sun is a perfect sphere on your sky. If I open up a bottle of perfume, if I take the cork out of a bottle of perfume, the molecules will drift out of the perfume bottle and spread around the room so that we can smell it. If I open a container of gas in outer space, if you've watched a science fiction movie where they open the airlock and they space someone, all the gas rushes out of the box and just disperses itself into space. Why don't the gas particles of the sun just blow away into space? Why does the... Sorry?
Is it because of the gravity that's pulling
right,
it in?
Sec. But at first that makes sense. The gravity's holding it together, but it must be doing a very fine balancing job, Arunsak, because the sun's radius is super, super sharp, as you could see in this image there. When you look at an image of the sun, a photograph, the edge of the sun is super, super hyper sharp. And that suggests that there must be a very delicate balance between gravity and pressure. And astronomers have a buzzword for this. It's called hydrostatic equilibrium. Hydrostatic equilibrium is a delicate balance between the gravity pulling the sun down and smushing it down, and that thermal tire pressure, that gas pressure pushing back against the gravity, so that they come into balance with each other. Introducing hydrostatic equilibrium. Hydrostatic equilibrium is a balance of forces between gravity pulling, let's say, in, and thermal pressure pushing out. Hydrostatic equilibrium answers the question, why does the sun maintain a fixed radius? And it is an important question because the sun is a ball of gas. Later on, you will discover as you study more stars that not all stars are in hydrostatic equilibrium. You'll discover. Oh, yes, Christopher?
That also why planets like Jupiter and Saturn also stay together.
Now, this is a great point, Christopher. Yes, Jupiter, Saturn, Uranus, and Neptune are balls of gas, so they also maintain hydrostatic equilibrium. But Christopher, since you're so on the ball right now, let me ask you a small challenge question. It's okay if you don't get it, but what about planet Earth? Planet Earth is not a ball of gas. It is in a version of hydrostatic equilibrium because its radius stays fixed. But Christopher, what would be the balance of forces that keep the Earth's radius fixed?
I want to say friction.
Not friction. Well, you need two forces to be in balance. Can you suggest what the two forces are that make the Earth's radius fixed? Not the strong force, Wyatt. That's at the nuclear level. Actually, why do I get to stand up in the gravitational field of Earth? Why can't gravity just collapse me into a puddle of atoms? I'm in a version of hydrostatic equilibrium. Or at least vertically anyways. It's not gravity versus gas pressure. It's gravity versus, yes, Wyatt, the electromagnetic or the electrostatic bonds between atoms. Wyatt's keyed into this here. He figured it out. Remember that in a solid, a crystal lattice exists where there are forces in between atoms. And those forces are ultimately due function F5, slide 3. Here they are symbolically represented by tiny little springs, but these little springs are symbolic representation of the electrostatic forces between atoms. These electrostatic forces also exist between the atoms and molecules in your body and in your bones. So your body stands up against gravity because of the electromagnetic forces of your bones. And likewise, planet Earth maintains a fixed radius because it's gravity versus the force of electromagnetism. In gas planets, in the sun and other stars, it's gas versus pressure. These are important concepts for us to think about. In fact, I'm going to burn just another second or two. I want to, just because I like to have fun. My office mate showed me these kind of cute little physics apps, and I want to share them with you because they can be kind of nice to build up your intuition. They have one here on gas properties. Now, this is a Flash application, so my computer might get annoyed with me, but let's see Okay, cool. It's going to work. All right, here we go. Let's learn about hydrostatic equilibrium in the ideal gas law. I've got a box. Let's pump it up. Pump, pump. Okay, here come the gas particles, and they're bouncing around. And let's keep track of our temperature and our pressure. Our pressure is about 0.8 atmospheres, 0.9. So that's pretty close to the same pressure of the air in this room that we're breathing. How does 300 Kelvin compare to the temperature of air in this room? I want to see if you guys remember room temperature in Kelvin before we go forward here. What is room temperature in any scale? What is your thermostat set to?
Kelvin.
Yeah, your thermostat is set to Kelvin?
Yeah, mine is. Yep.
You're a dweeb. No, mine is set to Fahrenheit, but I wish mine was set to Kelvin. That would be a little more badass. Someone's chatting me here. No, it's not, Kevin. The internal temperature of our bodies is different than the surface temperature of our bodies. Okay, go ahead. Someone tell me.
293.
Yes. Room temperature is usually 68 degrees Fahrenheit, which is 293 Kelvin. The point that I'm trying to make is right now for the gas particles in this box, they're pretty close to the temperature in your room, and they're pretty close to the pressure in the room. Let's do some funny things. I'm going to add some heat. What's going to happen to my gas particles when I add heat, students? They're going to go nuts. Austin, he's showing the particles go faster. But what's going to happen to the pressure, Austin? That's also going to go up. So let's do it. So here I'm adding some heat. You can see the temperature going up and the pressure is going up accordingly. Okay, let's add some ice and let's cool it back down. Okay. We'll add a little more heat. Can I get it to 293? All right, now I'm just being silly. Okay, so now we're at 1 atmospheric pressure at 293. What if I took little Mr. Robot here and I squished the box? What's going to happen to the gas particles if I squeeze the box?
Pressure goes up.
Pressure goes up. How about the temperature, a run sec?
It will go up too.
He's right. Let's do it. Okay, wait. For the gold, run sec, what property of the ideal gas law am I changing if I squeeze the box?
You're changing the number
The number
density.
density. Very good. This guy's on fire. All right, let's watch it happen in 1 sec. Here we go. Squeeze. Look at the temperature. Look what happened to the pressure. It went absolutely bonkers. Okay. Let's expand it. Something interesting happens when you expand. This is how the pistons in your car work, you know. If we expand it, it still kind of keeps a high temperature because it's isothermal. Okay, what do you think is going to happen? Let me cool this thing down. What do you think will happen if I add gravity to this box? Can anyone predict what will happen if I add gravity? Austin's freaking out. I don't know what's going on. Wyatt says it'll increase temperature, but watch this even more. Ready? Here's my bar for gravity. Let's do lots. Watch the temperature and pressure. Boom. Look what happened to the temperature. Did you see that? Did you see the temperature just went through the fucking roof? Excuse me. Pardon my language. Listen, I can even open this box up, and even though there's no container to the lid anymore, gravity, yeah, it forces a higher pressure at the bottom of the box, and the temperature went bonkers. This is why stars get so hot. Stars get hot because gravity squeezes them to be hot. Gravity squeezes the star. And when gravity squeezes, the temperature of gas particles go up. Eventually,
Isn't
the
that
star.
also like the core of the Earth?
I'm sorry, Christopher?
Isn't that also what's happening at the core of the Earth? All the pressure is like superheating it.
Right. The difference between the core of Earth and the core of the sun is the core of Earth is under a tremendous amount of pressure and high temperature, but it's not high enough to create fusion. Therefore, the Earth does not, it generates a little bit of internal energy, but not through fusion. The sun generates so much crazy energy that it can pump out a huge ball of light. And this brings me, I have time for one more module with you guys. I've kind of covered almost everything. I want to do here, just take some notes with me, okay? I'm freaking out. All right, first thing I want to do is I just want to write down the 6 layers of the sun so that we have them available today. And then I want to talk about energy generation in the sun. So bear with me, students. All this morning when I was waking up and trying to slap myself into consciousness, I was debating how I could cover all the little bits that I wanted to in this short time. The sun has 6 layers. And I need you guys to be kind of familiar with them before we do our homework today. We're going to make an analogy with a planet. The sun kind of has an atmosphere, it kind of has a surface, and it kind of has a core or an interior. The outermost layers of the sun are called the corona and the chromosphere. Taken together, these layers are kind of like the atmosphere of the sun. Although I use that analogy. Yes, that's how it goes in a survey course. Austin, there's so much to unpack. These things are very high temperature, low density plasmas. And Wyatt was alluding to that earlier. The temperature of the corona is like 1,000,000 Kelvin, and the temperature of the chromosphere is like maybe 10,000 Kelvin. I can't tell you everything about them right now, but I will show you. I will show you some quick, some hot takes here of those layers. Come on, baby. All right. So real quick, I'm going to fly ahead for a moment. The corona is a very high temperature, wispy outer layer of the sun. It actually generates mostly X-rays, but it actually is so hot at 1,000,000 Kelvin that it actually gives off some visible light. Now, we talked about eclipses briefly. I can't remember if any of you saw the total solar eclipse about a year ago, but when you see a total solar eclipse, you block out the sun's photosphere, and suddenly you can actually see light from the corona with your naked eye. Supposedly, it's very beautiful to see this. Notice that the corona extends out several solar radii. A better picture, if we just go here and do, get out of my way, total solar eclipse. So, oh, you were in a, wait, who said that? Who saw it? I just saw that. Wyatt, so you got to see it? Come on, internet, give me the total solar eclipse. So then
yeah, I also have a picture of it through the glasses.
No way.
Somewhere.
Yeah, you should find that and share with the class. So you got to see the corona. You saw this with your naked eye.
Yeah, I mean, yeah, it was like, because the sun didn't completely cover it, I don't think, or the moon didn't completely cover the sun, but on the parts that it did, you could still see it like part of the corona.
That's cool. I've never seen it with my naked eyes. And oops, sorry. Am I still recording? Yes. Okay. Moving on. So those are kind of wispy atmospheric layers. Then there's the layer that we think of as being kind of like the surface of the sun. And that's the photosphere. The photosphere has a key temperature. No way, man. That's good. I'm very jealous of what you got to see. The photosphere has a key temperature of 5,800 Kelvin. And the photosphere is a thin layer of gas, but what makes it special is this is the layer that all of the visible light comes from. That's how we define the photosphere. The photosphere is that layer I'm going to say this really lamely. That layer that produces visible light. I could have said that more elegantly, but I don't want to say it elegantly. I just want to be very simple. It's the layer that produces visible light, okay? The layer above it is too thin and too hot. The layer below it is too thick and too hot. This is the the porridge that's just right. It's the layer that produces the visible light. Then we have the interior layers of the star, which we're going to have to learn more about next time. We have the convection zone. We have the radiation zone. And then we have the nuclear core. Normally, when I introduce the layers of the sun, I spend a great deal of time talking about each layer. Each layer has its own physics associated with it. Each layer behaves differently. Energy is transported in different ways. And you can actually see these different layers depending on what wavelength of the sun that you look at. The photosphere produces visible light. The corona tends to produce X-rays. The chromosphere tends to produce ultraviolet light. The interior layers of the sun you cannot directly observe because you cannot see any deeper into the sun than the photosphere. You have to infer this through complex computer modeling and other methods. I'm almost ready to stop, but I have one last little quick note to take. Okay, Cameron, let me know when you're ready to move on. I'm sure you guys are ready for a break. I just want to take one last quick note so that our homework won't be too awful today. Okay, Cameron, are you cool, buddy? Cam? All right, Cam's already on break. How old is the sun? The age of the sun is the age of the solar system. How old is the solar system? How old
4
is the sun?
billion,
Pardon?
4 billion years.
Technically, it's 4.6 to the best of our knowledge. So the age of the sun is equal to the age of the solar system. And that age is 4.6 billion years old. Don't forget that 10 to the 9 is billion. The sun has been pumping out light for all of those billions of years. And the sun is generating a tremendous amount of energy, as you saw in last week's lectures. The luminosity of the sun is 4 times 10 to the 26 watts. And it's been pumping out that energy for all of those billions of years. How does the sun do it? The first myth that I need for us to dispel, sorry, I wanted to reduce the number of windows open. The sun is not a ball of fire. I'm going to keep this very short. Fire, my friends, is a chemical reaction. In a chemical reaction, molecules will change dance partners and energy is released in the form of light. You call that light fire, okay? So for instance, here I have some oxygen molecules. The red pellets are oxygen, okay? So I have two oxygen atoms. They make a molecule called O2. And if I mix 2 parts oxygen with 1 part methane, the black atom is carbon and the blue atoms are hydrogen. If you mix 2 parts oxygen to 1 part methane, you will get a violent chemical reaction where the atoms change their dance partners. Over here, you end up with H2O, and here you end up with CO2. That means chemistry is happening because the molecules are rearranging themselves. What is not changing are the atoms themselves. Hydrogen on the left is still hydrogen on the right. So fire means you change molecules, but the atoms stay the same. The sun could not be a ball of fire. I don't know if we're going to do this homework problem this week, but if the sun were a big ball of oxygen and methane, and you forced it to produce its energy at 4 times 10 to the 26 watts, the sun would burn out in like 10,000 years. So fire is not how the sun makes its light. You can also generate light through gravity. And while the sun did originally shine due to gravity, today, neither fire nor gravity can explain the light output of the sun. The sun continues to get its energy from nuclear fusion. That's the point that I wanted to make. I haven't gotten to get into the details of nuclear fusion. Cameron, stay tuned because we're going to calculate it in our office hours today. Okay? Our first question in our homework today is about nuclear fusion. That's going to be a chore because I haven't gotten to that yet, but whatever. Why don't we all take a little break because I'm sure you guys could use it. Let's take a 10, 15-minute pause, and then we'll tackle the homework. Does that sound like a plan? Okay, I like that too. It's even a little bit more than that, Christopher. You'll see. All right, I'll be back in a bit. Okay, everyone, I have an announcement to make. Is anyone there? Where's my peoples? Me and my glass of iced tea have made, hello, oh, you're not Austin. You can't trick me. Are you homeless too? Try to pull the old switcheroo on me, huh, Austin?
I stole her from Rhode Island, and now we're both homeless.
Sounds like you guys are doing okay. I made a command decision. This is important for any students who are watching later, especially. I've decided to change one of the homework problems. We were looking down the barrel at two of the homework problems were word problems that are very complex and take a lot of words to answer. And the first question we were supposed to do was on nuclear fusion and the strong force. And I just don't think that we've had enough lecture time on fusion yet for us to answer that properly. So here's what, trust me, this is going to be a good thing for our homework session today. Let it be known by fiat that one of our homework problems in homework 6 is about to change. We will no longer be doing question 47. So I want to put strike through on 47, but we'll instead be doing the question, okay. Open that in a new window and open that in a new window. We will instead be doing the question 55. That's not on there, right? Oh, 50. 55. Is 56 on there? Yes. 61. Oh. Okay. Instead, we will be doing the question on the color of the sun, 59. This is good for us because this is an easier problem than 47. Okay? Note 47 replaced by 59 at the last minute. Is everyone cool with that? Okay. Austin, can you read for us?
Let me just pull it up real quick.
Sure. I'm going to hide the trolls again. I'm going to go to speaker view. And we'll set up our homework as we always do.
All right, so I'm starting then with 40. I'm starting with 50.
Yeah, but hold on a sec. Why don't we all set up our homework in the proper way? So let's put our name down. Astronomy 1020 with your section, please, whatever it is. We are doing homework number 6. Am I right?
Yep.
And the homework is chapter 14 on the sun, 50, 55, 56, 59, and 61. I did that all from memory. I am awesome. Okay. Did I get that right?
55, 56, 59. Yeah, 16. Yeah.
Okay. So Austin's going to lead us off chapter 14, number 50. What's it say, buddy?
All right, hold on. Let me make sure. Okay, you can hear me. All right. Solar energy output, number 50. Okay. Observations over the past century show that the sun's visible light output varies by less than 1%, but its X-ray output can vary by a factor of 10 or more. Explain why changes in X-ray output can be so much larger than those in the output of visible light.
Okay, this question has a lot to unpack, and there's a lot for us to learn by solving and answering this question. Let me first ask you guys a question. What does the sun produce more of, visible light or X-rays?
X-ray.
False.
Okay.
Let's see why. I knew you were going to say that. That's why I asked the question. The sun does not put out more X-rays than visible light. And that's because the sun ultimately is a black body. You guys will remember that in chapter 3, you learned that black bodies are hot, dense thingies that produce white light that's like a rainbow. But I also taught you, maybe even in our last lecture, that the sun does not produce all wavelengths equally. Slide 76 here, let's try that again. Slide 76 here shows us that for a hot, dense thingy with a temperature of 6,000 Kelvin, the sun will emit a radiation profile that is a black body spectrum which has a peak here, but that the sun is producing light all across the electromagnetic spectrum. Now, this is a cartoon version. Allow me to level up and show you the adult version of this graph. It's the real version of the sun's light output. Here we go. This is a wonderful graph showing, and this is some real stuff here. This is the real, this isn't like Kitty 101 stuff. This is the adult slide. It's a plot of intensity of light on the y-axis. In other words, the brightness in watts per meter squared. So this is brightness. And on this axis, we are plotting wavelength in nanometers. First of all, let's make sure that you guys can orient yourself in this graph. The green curve shows you an idealized black body with a temperature of 5,800. That's how a hot, dense metal would glow. The black curve shows you the real spectrum of the sun. And the first message that you're supposed to take away is that to a very good degree of approximation, the output of the sun's radiation is very close to a perfect black body. It's not absolutely perfect. There are some absorption lines here, and there are some emission lines there. But for the most part, the energy output of the sun in terms of its light matches up with an ideal black body. Class, tell me, where is visible light on this graph? Caitlin's looking it up. Where would the visible light be? Someone's chatting me. Not just, oh, Blair for the win and Cameron for the win said what I want to hear, except Cameron's is better because he used units, Blair. 400 nanometers to 700 nanometers. Aw, this is the visible light here. Where are the X-rays, students? What are the range of wavelengths for X-rays? Hot shots? Oh, someone knows? Well, then look it up. Didn't I give you some notes about this? Okay, let me. Here it is. Cameron, not to 150-ish. Yes, a Runsack has it right. 0.1 to 10 nanometers. Let's go. So a Runsack, where are the X-rays then? Show me whereabouts on this graph. And talk to me so that students who are listening later can understand.
So it looks like it's like in between the 0 and the first little spiky.
Like over here, right?
Yeah.
So a Runsack, how would you say the visible light output of the sun compares to the X-ray output of the sun?
It's a lot more.
A lot more visible light than X-ray light, right? Well, a Runsack, then I'm getting kind of confused. What the hell did this question ask me then? Because it sounded for a second like the question was saying, why does the sun put out 10 times more X-rays? But now that my reading comprehension is getting better, not everyone could be a star child. Okay. What's the question asking me, students? That's what I'm trying to say, is what is this question actually asking of me? Austin, you read the question. What's the question asking?
Can you hold on? Can you repeat that for me? I'm sorry.
You read the question, chapter 14,
Yeah.
number 50.
I
don't
did
think
that.
I understand what it means. I don't think I even understand what it's asking me.
So it's asking you. Hold on one second. Graham, hold on. I'm in class. I'm answering the question. Okay. So it means. Give me 1 second.
Yeah.
It means that no, not you. Observations over the past century show sun's visible light output varies, so it's pretty consistently outputting the same amount of visible light, but its X-ray output can vary by a factor of 10 or more. So maybe hold on 1 second.
You're right there. You've got your finger on it.
The corona layers where all that crazy shit happens with all the X-rays, so it's probably highly variable. Well, that makes sense. That's exactly.
No, that's exactly right. You're saying all the right things.
Okay.
Okay. The
And
question, Austin,
why change the X-ray output could be so much larger is because it's more sporadic and it's different types of outputs and stuff.
Yeah. So the question's asking about variability. It's not saying why are there 10 times more X-rays. It's saying why does the X-ray emission vary? Let's make a little graph as part of our answer so that I know that you guys understand the question. This graph is going to be a graph of light output versus time. So take a ruler and make yourself a little y-axis. And then make an x-axis that's a bit longer. This is going to be the brightness in watts per meter squared. And this is going to be time in years And since it said over 100 years, we'll go from 1900 to 2000. Let's let my black marker represent visible light. And because X-rays are short wavelength, I will use purple for the X-rays. We've already discovered that the sun puts out a lot more visible light, but we know that it's only varying by 1%. So up at the top of the graph, we'll draw a line that's almost straight, but we'll show some really tiny wiggles at the 1% level. Then we'll represent the X-rays with purple. They will be lower in intensity because there's way less X-rays. Runsack just showed us that. But the X-rays will be highly variable. And here's the thing I didn't mention today. They vary tremendously with the solar magnetic cycle. So my X-rays are doing something like this. They're having crazy spikes, and then they're dropping. And they're having crazy upticks, and then they're dropping. And every 11 years, we flip the cycle, a maximum and then a minimum. All right? And the book tells us that the maximum is a factor of 10 times greater than the minimum X-ray output. One thing I don't like about this is that we're trying to compare the visible light and the X-ray light with different, I don't know if I want to say units, but in this case, we're using percentages, and in this case, we're using factors. My first question to the class is, what if I had to represent a factor of 10 as a percentage? What would the number 10 be as a percentage, students?
Would it be 1000%?
Exactly, Austin, because you, as any good banker knows, you move the decimal place twice. So you're kicking ass there. So I think that's more helpful because you can see that if you put them on the same scale, X-ray fluctuations are 1,000 times greater than visible light fluctuations. Now, Austin, you are really killing it today in ways you can't even understand. You also suggested the answer to what's causing these fluctuations, and you made a pretty good first pass. What was your idea about why these things are varying?
Because there's the solar flares, like the actual output itself in the X-ray light is kind of savage. So
right. So one is the processes. The solar flares do produce a lot of X-rays, but you also mentioned during your earlier answer that the different layers are so which layer is producing the X-ray light?
The corona layer.
Very good. And which layer is producing
the photosphere? The photosphere.
Exactly. So they're coming from totally different layers. Now, here's the part that you guys might not be ready for yet, but Austin and friends, you've already done so good. You've already impressed me so much today with your intuition. I'm gonna ask you one more question. The process that produces visible light in the photosphere is not the same as the process that produces X-ray light. I didn't get a chance to explain that to you, but I bet you guys could guess what's producing the visible light, or I want to see if you can guess it. Why is the photosphere producing visible light? What's the mechanism by which it does this?
It's because of the ratio of the hydrogen and helium different in their reactions.
In fact, no, it's not about chemical compositions. Hydrogen and helium do not react with each other, Runsack, because helium is a noble gas. Helium is not reactive at all. If you had a box full of hydrogen and helium gas, they would just be this colorless, inert gas that did nothing. No reactions at all. Chemical reactions are not the reason why the photosphere is shining.
Is it where it's placed?
Magic. No, Blair, there's no such thing as magic. There's only science. Here's a hint.
All the energy is being added, and we were talking about before how the electrons change their energy levels, and maybe that's
when you're doing emission. What type of spectrum would the sun be if you looked at it with a spectroscope?
A rainbow.
pretty close to a rainbow. And a rainbow is what type of light production?
Visible light.
It
Yeah.
also produces infrared and ultraviolet too. Yeah, continuous. There's another word for continuous. A radiation spectrum that is continuous is a no, not full line. It's black body radiation.
Oh, you said that.
Yeah, but I don't think you understand what I mean by that. Black body radiation means
temperature.
Thank you, Christopher. Christopher understands me. I glow because I'm hot. The photosphere produces visible light that's constant because it's a constant temperature, and it is the temperature of the gas that makes it glow. But that's not what's producing the X-rays. In fact, before I tell you the answer, which I'm just about to do, let me go back one more time to this slide, or this, oh, sorry, this is the wrong slideshow. Let me go back to the slide where I showed you guys the sun at X-rays. Oops. This video that you're watching here, this video is showing you an X-ray image of the sun. First of all, let me ask a question. What color is the photosphere in this video? That's a very illuminating answer, should we say. What color is the photosphere in this video?
Yellow.
False.
Violet.
False.
No, indigo.
False.
White.
No, look at the surface of the star. What color is it?
Gold.
Orange.
Okay. I see what's going on here. You guys are confused. Yes, Blair. Blair finally got it, but this is not the surface of the star. That is the surface of the star right there. Let me clear this. That is the surface of the star. This is the corona. So Blair, once again, Blair, what color is the surface of the star? Black. The surface of the star is black here because this is an X-ray image of the sun. And guess what? The photosphere doesn't really produce any X-rays because as Arunsak saw, X-rays are barely even produced in a blackbody spectrum. Where do we see the greatest amount of X-ray? Oh no, corona, I forgot about the, man, everybody's getting it. The corona, I forgot. When you guys were freaking out earlier, I forgot. My head was in the sky here. Where do we see the greatest X-ray emission? In the corona, but near what process? Oh no, Cameron, you have it? Oh geez. I knew that some of you guys were going to get this. And you know what? For all I know, I'm going to get it, and we're all going to be in trouble. Yeah, be safe, guys. Rona children. I don't want to be Rona daddy. Okay. I want to be Corona daddy. That's what I want to be. All right, listen. Okay, inside joke. Anyways, where do we see the greatest amounts of X-ray light coming in this video, students? Where do we see the greatest amount of X-ray emission coming from? Thoughts?
I mean, it looks like it's coming from the surface. It looks like it's sprouting from like an increase of energy almost underneath or right on the surface. It gets sprouted out.
Yeah, Christopher, what were you going to say?
Are those sunspots?
They are sunspots, but you know what? You guys don't have all the puzzle pieces here. The magnetic fields are like loops, and the magnetic fields get more intense the more bunched up the loops are. So they are actually connected to sunspots, Christopher, because where the magnetic fields get really knotted up, that's sunspots are here and here and here. but the sunspots are a little bit lower, Christopher. Where we see the greatest amount of X-ray emission is where the magnetic field density is highest. Basically, X-rays are being caused by interactions between plasma and magnetic fields. So I guess it's an unfair question, but I was hoping you guys would say, oh, it looks like wherever you have crazy magnetic field lines, that's where we see a lot of X-rays from, okay? X-rays come from magnetic field storms. All right, let's answer the bloody question. I've teased this out for too long. All right, I need to erase this, and we're going to answer this with a paragraph. You guys ready? I'll take that as a big bet, yes. X-ray emission from the sun is so much more variable than visible light because X-rays are produced at different layers by different processes. Now we're going to take a sentence or two to describe each layer in each process, okay? X-ray emission is produced in the sun's corona. By the way, the coronavirus is named after the corona, the sun feature, right? Not the other way around. Okay, just want you to know who was there first. All right, the X-ray emission is
Spanish
produced,
for crown.
right. And the virus apparently has a little crown on it that looks like the sun's corona. If you look at the coronavirus, it looks like the sun during an eclipse. It has a little crown on it. X-ray emission is produced in the sun's corona, where high temperature plasma particles interact with twisting magnetic field lines to produce bursts of X-rays. As the magnetic storms, we'll kind of call them magnetic storms. As the magnetic storms fluctuate with the sun's 11-year solar magnetic cycle. We're going to underline the term solar magnetic cycle because it's kind of a big deal. As the magnetic storms fluctuate with the sun's 11-year solar magnetic cycle, so does the X-ray emission vary. Now we'll address the visible light. Visible light on the other hand is produced at the photosphere. By, all right, it's getting harder to write at the bottom of the board here. I'm glad I'm doing something right. Visible light, on the other hand, is produced at the photosphere by thermal blackbody radiation. Thermal blackbody radiation. Dot, dot, dot. I'm going to need to go back up here. Let's take a pause to see how can I erase up here? How's the class doing? I know you guys are lagging behind me. I'm going to take out this first paragraph, okay? Is everyone cool with me just taking out this first sentence here? All right. Let me collect my thoughts. Visible light, on the other hand, is produced at the photosphere by thermal blackbody radiation. Because the photosphere's temperature remains constant at 5800 Kelvin, so does the visible light remain constant with only a 1% variation due to blank. My question is, can you fill in the blank? The sun's visible light remains constant with only a 1% variation due to. Can anyone think of what might be causing microscopic fluctuations? Being a scientist means being the ultimate badass. You have to be able to write, read, and do mathematics, right? Yeah, the heavy metal. No, not the heavy metals. Sorry. Let me go back a couple. What might be causing the 1% fluctuation in the sun's visible light output?
Location?
Blair, say it loud and say it proud.
It's sunspots.
Woo! That's right. See, you do have that's right. It's the sunspots which cause the microscopic variation in visible light. Okay. Take a moment to catch up while that's okay. Take a moment to catch up while I drink my iced tea here. Here's to you. You guys can see why I wanted to nix the other word question today. I think one of those was enough. No, Daniel. I particularly swapped out questions to make sure the other ones are faster and easier. Yeah, sign up for my other classes. I need that. I'm ready to move on when you guys are. I just need you to let me know when you're done writing. Okay, everyone needs a second. Yeah, where is Devlin? Okay, I'm feeling like, are we all caught up? Does anyone need more time on this? Oh, Cameron, let me know when you're good, buddy. Okay, Cam. Okay, can we do this? Let's do it. I don't know. I don't know what that acronym means. Okay. So I think earlier Blair was indicating that she wanted to read a problem because she never gets to, read out loud for the class. Wasn't that right, Blair? Wouldn't you say, Blair, that you're dying to read? I'm confused. All right, will somebody read me the damn problem? Come on, Blair. Do your civic duty. Chapter 14, number 55.
You want me to do it?
Please, would you?
Yeah. The title is Chemical Burning and the Sun. Here, let me know when you're ready.
By the way, chemical burning means fire. This question is designed to prove to students that the sun could not exist as a ball of fire. Okay, hit me, Runsack, that was you.
When an object burns in a fire, the amount of energy released through this chemical burning is typically about 10 to the 8 joules per kilogram of mass burned. Use this fact to estimate how long the sun would last if its energy source were a huge fire releasing chemical energy.
What they've done is they've told us the amount of energy per unit mass that the sun can produce. Sorry, let me try that again. They're telling you the amount of energy per unit mass that fire can produce. So if you burn a log and you're basically reacting oxygen and carbon, you're producing up to 10 to the 8 joules per kilogram for each kilogram. Where's my reference kilogram? For each one of these, you can produce about 10 to the 8 joules. Okay, we're going to have to use some. This is the thing about problem solving. Sometimes the givens are hidden. Sometimes the givens are not given. But you have to be a smart person and say, what do I know about the sun? What are some facts that would help me here? So here's the sun. The sun's putting out some energy in the form of light, right? And we know that it's burning 10 to the 8, or it's producing. So this is a sun that's on fire. We're basically imagining a big ball of fire. And it's producing 10 to the 8 kilograms, or 10 to the 8 joules per kilogram, excuse me. What other givens might we use? We know its mass, Cameron. The diameter is going to be less important, but the mass of the sun will certainly be helpful here. Because if they're giving us the amount of energy per kilogram, we'll probably want to know the number of kilograms that we have as a reservoir. 2 times 10 to the 30 kilograms from today's lecture. Now, what was the ultimate thing they asked us for, Runsack? The question said to calculate what?
How long would the sun last if it was a ball of fire?
So in other words, we're looking for some unit of time, like seconds or hours or years, right? Can you guys guess what the other hidden given we need to use is? What will determine how quickly the sun uses up this energy?
Would it be temperature? No.
Good guess, but not in this case. How is the energy lost from the sun, Arunsak? Where's the energy going?
It gives off photons, light.
Exactly. So what parameter of the sun parameterizes the energy, the light energy that it gives off? Look at the fixed dimensions of the sun from your lecture notes today. Wyatt's got it, the luminosity. Very good. And the luminosity is 4 times 10 to the 26 watts. By the way, can you guys remind me what a watt is again? What's a watt?
Measurement of power?
Sure, but what other units does it resolve into? I saw someone in your background, Emily.
Hertz per second squared.
No one's really said it right yet. A watt is also the same as,
Is it joules?
it's not joules, Emily, because joules are energy and watts are power, but it's close. You're close, but you're no cigar.
I got you. Joules per second.
That's what I want to hear. Okay.
Wait, did I just steal that, Austin?
Everyone's
Yeah, you just fucking stole it, but it's fine. I'm just joking.
I love you, bro.
Now listen, I'm trying to teach you something here. This problem has an astronomy point, but this problem also has a problem-solving point. I want to show you how the pros would approach this. I'm about to teach you, wait for it, dimensional analysis level 2. Okay? Dimensional analysis level 2. In dimensional analysis level 2, you try to figure out the formula, or you try to figure out what to do by using the units and jiggling them around to get your final answer. So we're going to set up some division bars, and we're going to get to our final answer. And what units do our final answer want to have? This is like a game, all right? Let's think in terms of units. When I get my final answer, what units do I want that answer to have?
Well, if our question is how long in a unit time,
Right. So not kilograms, Cameron, but Wyatt, what should my units be?
would we use like seconds?
Since you have seconds on the board, that's a good place to start.
Okay.
Wait, so Cameron, what we're looking for is how long can the sun shine its light if it's a ball of fire producing 10 to the 8 joules per kilogram? We know the reservoir of kilograms, and we know how quickly it's shining out the light. So Wyatt or anyone else who feels brave, you've got 3 quantities to work with. This one, and this one. Can you figure out a way to jiggle them around so that you only end up with seconds through dimensional analysis? Do you understand? This is how professional scientists solve problems this way. They let the units do the work for them.
Well, I mean, the first obvious thing would be that the equation or the number for fire and then the number for mass need to be on like opposite sides of the bar.
Wyatt, I like what you're saying so far, but could you talk to me in terms of units rather than numbers? Everything you said is correct. But
Okay,
now
yeah,
say the
so-
same thing again, but units.
The joules over kilograms, that one needs to go on the top. Or
So,
yeah.
Joules on the top,
Okay.
kilograms on the joules
I like
per kilogram on the top is the same as this, right?
Okay, I like that.
Right.
And then next we could do the kilograms.
Killer. So the
Then on the top.
kilogram will cancel out.
Yep. And then we have joules that we're trying to cancel out again. And the last equation that we have is joules times seconds. So then would be joules over seconds on the last one, right?
Wait, which goes on top and which goes on bottom?
joules goes on the bottom, and then seconds goes on top.
Yeah.
Seconds over joules.
That's exactly what I wanted him to do. I wanted him to wiggle these units around. And Wyatt, what is so cool about this technique is you really didn't have to think about anything except the only way this is going to work is if all the units jiggle each other out so that I end up with time. Now, Wyatt, complete the job. You're doing great by putting the numbers in the right positions.
All right. What? No. Okay. So then it would be 10/8 on the top, or would that be on the first number that we're
Wait,
starting
10/8?
Well, the 10 to the 8th on top.
Okay.
And then for the next bar, we can do 2 times 10 to the 30th on the top. And then 4 times 10 to the 26th next to seconds on the third bar.
Now you fucked up.
I did.
It's 4 times 10 to the 26 joules per second.
Oh, okay. So then you have to put that on the bottom because we're dividing because we flipped it.
In 1 second, you produce 4 times 10 to the 26 joules, right?
Yeah.
Does that make sense? Because you
It
flipped
does.
the units upside down, you have to flip the number upside down. All right. Hey, Wyatt, since you're so good,
Yes.
can you do this in your head?
Do it in my head. 10 to the 8th. So then 2 times 10 to the 38th. And then
What's 4?
2, what was that?
2 divided by 4 is 1/2, right?
Yep. So we have 0.5 times
10 to
10
the
to
38 minus 26.
4th. And then we have to move it over. So then the third. So yeah, 5 times 10 to the third.
Right?
Yeah.
Okay. Wait a minute. Something is wrong. No. We did something wrong somewhere. 38
Okay.
minus 26 is not 4.
Oh, it's 12. I was thinking because we were doing 30. Yep.
Yeah.
Okay.
I would have done that too. All right. So if it's 5 times 10 to the 12 seconds, it's also the same as what? 0.5 times 10 to the 12 seconds is the same as.
5 times 10 to the 11th.
Killer. I like your moves. That's how the pros do it. Now, our answer is 5 times 10 to the 11 seconds, class. But I think the answer would be more interesting expressed in years. So, Emily, if I can impose on you, will you help me do dimensional analysis to convert 5 times 10 to the 11 seconds to years?
Okay, so you'd have 5 times 10 to the 11 seconds and then multiplied with the line. So you'd convert it into minutes first, so minutes on the top and seconds on the bottom.
Okay.
And then the next one would be minutes with hours on the top. And then days on the top. And then would you do years or would you do it by months?
Years. Months are a sucky unit because there's not a consistent number of days in months, right? Sometimes it's 30s. So months should be avoided whenever possible. Okay, now help me fill in all the numbers on the bars, please.
So there's you put 1 minute and then 60 seconds. And then 60 minutes and 1 hour. And then 24 hours in 1 day. And then 365 days for 1 year.
Okay, class. Take out your calci and punch it up. Nicely done, Emily. You had some smooth moves there, kiddo. I'm feeling good about you going into this exam. If you can do what Emily just did, then you are mastering this course. Oh no, what did I do with my cap? No! I just opened this fucking thing. Oh, I've got a dirty mouth today. I am a bad boy. Oh, there it is. It's all right. Okay. What do you get?
16,000 years.
Yeah. Okay, so Christopher, sorry this is so low, guy. I'll do it over here. Ain't even got the game. You got the game. All right. Christopher, if you can, why does the answer of 16,000 years, why does that suggest that the sun is not a ball of fire? Why cannot the sun be a ball of fire?
Because it's a lot older than that.
Right. Now, 16,000 years might be enough to explain the universe in some books, right? Some books claim the Earth is only 2,000 years old, but we won't talk about that, okay? Oh, Austin got kicked. Plus, yeah, plus there's no oxygen. Well, there's not a lot of oxygen in the sun. We know that it's hydrogen and helium, so it's already a silly thing. But the point of this question is, you know, when people talk about the sun, if you go back to time immemorial, if you think about like the way the Greeks would talk about the sun, Helios would race across the sky in his fiery chariot. But the sun can't be a ball of fire because at the amount of energy it's pumping out, it would have burned itself out in 10,000 years or so. The cool thing about nuclear fusion, as you discover in the next problem, is it's a very slow burn that can sustain energy output for billions of years. Yes, you can see the board. I'm talking. I'm sorry. I'm yapping. Okay, when you guys have this down, we can move on to the next one. If you want to add a funsy note, just put, the sun is not a ball of fire. Blair, are you okay now? Can we erase? Does anyone object to me erasing? I'm erasing. Caitlin, are you down to read one for us?
Sorry, it like took me a second to what's it called, my thingy?
Yeah.
Unmute it.
Unmute.
All right, thank you very much for that
Okay.
I do see
What question number is it again?
56.
56. All right, pulling that John up right now. All right, so lifetime of the sun, the sun's chemical composition was about 70% hydrogen when it formed, and about 13% of this hydrogen was available for eventual fusion in the core. The rest remains in the layers of the sun where the temperature is currently too low for fusion. Do you want me to read part A?
Not yet. Take a moment to get this down, Caitlin, and I want all of us to draw a little picture. Let's draw a sphere here representing the sun. Only the hydrogen can fuse in the sun. But not only can the hydrogen only fuse, but only at the core where the sun is hot enough can the hydrogen fuse. So if we're going to try to calculate how much fuel, this question is kind of like, how much fuel does the sun have? Let's say 70% is kind of close to 75%, which is 3/4. So you've seen I've drawn a quarter of the sun off. So a quarter of the sun is helium. That quarter cannot be used for fusion. Hydrogen. And that hydrogen can be used for fusion, but only the hydrogen that is hot enough can fuse.
Name of the person
In
who
other
would like
words,
to act as your beneficiary.
hydrogen, which is in the core, can be used.
Right. This would
The
be
red dots,
on head.
that is the stuff that's
Please take down the beneficiary's first name.
Our goal is to figure out how long the sun will last by calculating how big that reservoir is.
Okay, so their first name is Nature.
Geez, Caitlin, it's noisy in your background, huh?
Oh, sorry, my cousin works
That,
down here with me.
that's okay. I was just going to say that must be difficult to concentrate. You know, something students need to learn that's important is when you have a place to study at home, this is important for the regular semester too. Having a sacred place, we don't all get this luxury, but having a sacred place where you can focus and concentrate is really important to doing well in school. So always try to, when I lived in the dorms, when I was at the University of Arizona, it was like freaking madness there. There were kids doing the backstroke on magic mushrooms down the hallway. It was like a big rollicking party there. So I would have to go to the library to find my quiet space. And I did so much of my work there. So I was very grateful. For, well, it was a good time until you had to do your homework. And then it was a real difficult time. Anyways, I'm just yapping. Okay, Caitlin, go ahead and read us question A.
All right, going back to it. Question A, use the data and the sun's mass to calculate the total mass of hydrogen available for fusion over the lifetime of the sun.
With this information.
Wow, I can't spell.
It's okay, me neither.
With that form.
Available for fusion. I always like to see before I tell you how to do it, if you guys could figure it out. Does anyone have any ideas out there in the television audience about how we can calculate what the number of kilograms are available for fusion in that little red zone there? What should I do? Remember that we know the mass
Find the size of the little red zone,
or
or the area of the red zone.
Hold on, I'm sorry. Could you say that one more time?
We have to find the area of the red zone.
Oh, we don't even need to find the area because
No?
they've given us the percentages in the problem. It's actually way simpler than that, Wyatt.
Okay, so then we can just take the 13% hot hydrogen and multiply that by the mass.
Well, that will give you the percentage of the hydrogen that's hot. But remember, not all of the star is hydrogen. A quarter of it is helium.
Okay, so then we need, okay, so we have to multiply first the entire mass by the 70% hydrogen, and then
Yes.
the result of that by the 13%
Right.
hot
So
hydrogen.
when we multiply by 70%, that knocks out the helium. Then we multiply by 13%, and that gives us the inner part. So excellent. So we're going to multiply by 0.7. Actually, let's set this up better. The mass of the sun is 2 times 10 to the 30 kilograms. The mass available for fusion is 2 times 10 to the 30 kilograms times 70% times 13%. Go ahead and get that for me, guys. Two sig figs will suffice here. I am
1.8. You
Sorry?
ready?
Yep.
It's 1.8 to the 29th, or times 10 to the 29th.
Thank you. And that's kilograms, right?
Yep.
All right, box that. Caitlin, once you've got that down, read us B.
Gotcha, covered. Okay, part B. The sun fuses about 600 billion kilograms of hydrogen each second. Based on your result from part A, calculate how long the sun's initial supply of hydrogen can last. Give your answer in both seconds and years.
How many zeros are in a billion again, Caitlin?
9.
Okay. They want us to use the reservoir of mass, the stuff in red. They also are telling us the fusion rate. The sun's fusing 600 billion kilograms per second. We need to end up with a unit of time. How long? Let's use the same technique that Wyatt used last time. Let's use dimensional analysis to tell us how to get there. Do you guys know how the game is played now? How do we do this? A run sack. How do you think we should do this?
So you take that 600 to the 9th times the 1.8 times 20. Well, units first, my bad.
Yeah, because if you
X
did
bar.
that, if you did that, you'd end up with kilograms squared per second. And I don't think that's what you want.
Take the X bar.
Yep.
And then we want seconds, right?
Yep. Okay, so now put the units in such a way where that happens.
So in the first one, you got kg on the top and S on the bottom, right?
I don't like it.
And then
I don't like it because you only have one S. And if you start off with your S on the bottom, you're kind of screwed getting it up on the top, right?
so we flippy.
Yeah, then we flip it. Okay. Okay. So
S top, kg bottom. Yep. And then you want the kg on the top on the right side.
Okay, now can you put the numbers in for me?
Yep. You want the 600 times 10 to the 9 on the bottom where the kg is. And then the 1.8 times 10 to the 29 on the top, on the right side.
Yeah.
On the right side. And then, yeah.
The one thing I would do just to the point of class is it's 600 kilograms, 600 billion kilograms per 1 second.
Okay.
But
see you later, bro.
Okay, so in other words, if we divide the mass by the rate, that'll give us the time. Go ahead and punch it, guys.
Uh, 3 times 10 to the 17 seconds.
All right. They want the answer in both seconds and years. Obviously, it's a lot more interesting to ask how many years will the sun shine. Christopher, do you remember that at some point I gave you guys the number of seconds per year? I actually had you guys work it out on one of the first lectures. Who knows the number of seconds in a year? No, definitely not Blair. Way more than that. No, Cameron. Look it up. It's in your notes.
I know it.
Wait, someone. Yeah, what is it?
Okay, it is 31,536,000.
It's pi times 10 to the 7 seconds. It's 3.15 times 10 to the 7 seconds per 1 year. That number will really, really help you on the test. Knowing the number of seconds per year will save you a lot of time.
Is that on the sheet you're gonna give us?
That's bonus. I think sometimes I put it on the sheet, but sometimes there are bonus things that I don't tell you. And if you're a really good student and you know them, then you get rewarded. Let me get out of here. Where was that formula sheet? I gave that to you guys last time, right? Where's my damn Dropbox? CCRI 2020 fall? Wait, no, sorry. Wow, my brain is slow today. It's very slow. Is that on the midterm formula sheet? No, but you know what? Can I tell you guys something funny about the exam? My exams, when I have class in person, they're not open book or open note exams. You just get this one formula sheet and that's it. Don't be shy, show us the exam. But what's cool about doing this thing online is I really cannot even begin to try to police you guys. So in some sense, it's open book, open notebook. If you're going to cheat, then everyone's got to be able to cheat equally. So yeah. All you got to do is guess my password, bro. You guys would put more time into hacking my password than you would studying for the test. That is the quintessential essence of students right there. Okay, so how many years are we talking?
9.5 billion.
9.5 times 10 to the 9 years. Put a box around that as well.
Hey, Professor, my friend has a question for you.
Yeah. Hit
Do
me.
you have my friend in your class?
Who's your friend?
Hi. His name is Joe. I don't know how to pronounce it. Joe.
Oh, well, it's hard for me to see, and if he doesn't if he doesn't share his video with me, then he's just a troll.
I saw a picture of you on Snapchat and I was like, oh my God, I know who that is.
Well, tell him I said what's up and share your video, bro. Okay, hold on. We got one, by the way, mildly, yeah, Rhode Island famous. That's good enough for me.
There's like 11 people who have heard of you.
Well, no comment on that. Anyways, 9.
Professor, are you from Rhode Island?
Yeah, I am. I'm a Rhode Islander, just like many of you are.
Wait, didn't you say you were in a band at some point?
I am in a band. I'm still in a band. Yeah, that's what I do when I'm not teaching you guys. Is I play my synthesizers.
Drop the name.
Triangle Forest.
You play. Is the other half of your apartment a band?
As a matter of
Well,
fact,
not a. Like, I don't think your apartment is a band, but set up for a band.
the other half of my apartment is filled with stuff like this. One thing I love about synthesizers are a place where art and science come together. You're not playing an acoustic guitar or a didgeridoo. You are playing electrons inside of a box. You are shaping the waveform and the signal itself.
That is the most Professor Britton thing I've ever heard in my entire life.
When I taught you guys about waves last week, when I taught you about frequencies and energies and hertz and all that stuff, those waveforms are what you're sculpting and shaping inside of a synthesizer. It's like you're playing math. It doesn't get any better than that. Well, I don't know. I don't want to proselytize my crappy little band, but you know.
No, don't be shy. Let's hear a little bit. You're teaching us about electron. Like, this is helpful.
It's on the website.
Well, I may or may not have a show coming up, so if you can figure out where it is, then you can come and see it.
I think there was an extra question that we could just take out and replace that with a little bit of music.
Oh no! Once I've done that, I've totally jumped the shark. Look, let's just finish this homework because I'm sure other people have better things to do. But we can talk about the bandit sometime if you want. 9 billion years. Okay, Caitlin. But I play out all the time. There's plenty of opportunities to hear me. It is what it is. What was part C, Caitlin?
1 second. Okay, part C. Given that our solar system is now about 4.6 billion years old, when will we need to worry about the sun running out of hydrogen for fusion?
So this is, yeah, for real. All right, so fine. I'm playing a show next week at dusk on Friday. But
Paula, we're gonna go. We're all gonna pull up.
that's great. That's great. That'll make me very popular. That's what all the slimy club owners are always saying. Make sure you tell your students about the show, you know.
Big facts. We're all getting drinks.
So this is a real easy problem. You've got a total lifetime of the sun of 9 billion years, and the sun is 4.6 billion years old. So how long do we have left? No, not karma at dusk. It's a dirty little rock and roll bar called Dusk. It's very cool. Um, 9.5 billion years, 4.6 billion years old. How do we do it?
Subtract the 4.6 billion from the 9.5 billion.
Exactly.
I think I got.
And what do you get?
Is that 8.5? That doesn't make sense.
9.5 minus 4.6.
Okay, I got 8.5 billion.
Wait, how can 9.5 minus 4.6 be 8.5? That don't make no
Oh
sense.
no!
It's 4.9.
Oh, sorry. Oh yeah, 4.9 billion. Thank you. I'm trying to like concentrate on the chat and you guys talking to me. I'm getting confused here. 4.9 billion years old, or left. 4.9 billion years left. So earlier, someone asked during the course of the lecture, how much time does the sun have left? 5 billion years. You got some time before the sun dies.
It's middle-aged.
It's middle-aged, right? We're right in the middle of the sun's lifetime. Okay, let's see. That's 3 down. The last 2 are pretty easy. I've been goofing off with you guys a little bit too much today. It's been fun though. Okay, so 4.9 billion years left. Get all that written down so I can erase. Can I erase? All right, I'll take that as a yes. Sorry, I was getting distracted again. All right, let's see. 59 is a quick and easy one. This is the one that I swapped out our first problem with. Christopher, you down to read?
Yes.
Okay.
Okay. The color of the sun, use Wien's law, and the sun's average surface temperature of about 5800 Kelvin to calculate the wavelength of peak thermal emission from the sun. What color does this wavelength correspond to in the visible light spectrum? Why do you think the sun appears white or yellow to our eyes?
All right, so we've got 3 little questions to answer here. We got to find the lambda max, the peak wavelength. We've got to find out what color that is. And then we have to address the white versus yellow color of the sun. Remember that Wien's law tells us that the peak wavelength of any black body is 3 million nanometer kelvins divided by the temperature. So what do I do, kids?
You divide the 3.63 times 10 to the 6 thingy by the temperature of the sun.
Okay. So we'll put in 5,800 Kelvin. And what do you get? Kelvins cancel. You know, during a normal time, the shows you can just kind of show up to, and we would play inside. Things are a little weird because of COVID and the social distancing thing. We're going to be playing outside, like in the parking lot. So it's actually a free show. And we're going to play in front of a giant wall that has a projection on it, and people kind of sit in isolated seats. I'm not sure if it's going to be cool or cold or what, because it's going to be outside, so it'll be a little chilly. And normally people dance at our shows, and I don't think that's going to be possible. So I think this is going to be kind of a weird one, to be honest. But I'm honestly just,
Hey,
it's been.
Sound travels better in cold.
Well, that's a point. So that will be good.
Where are you guys playing?
At a club called Dusk. It's like
Okay.
down in Oneyville, or like
Whether are you playing?
deep in the west side. Oh, I don't know the time, like rock and roll o'clock, like 9, 10.
But Professor, like, you can give me a date. You know,
I'm comfortable proselytizing my show in this
like
format.
October 31st.
I've already done it though, so it's Friday, October 16th. Okay.
27th, I got.
Did it. All right. What's
Well,
the
Facebook says the 27th.
12. Okay.
No, that's not it. I don't think I've put it up. It's supposed to be October 16th.
Okay.
I'm not very good at updating my social medias, guys.
What are your social medias?
What's the peak wavelength?
517 nanometers.
Okay, what color is 520 nanometers? Social medias. What color is 520 nanometers? My electromagnetic wave lovers.
Indigo?
No, actually, it's a bit longer than that. Let's call up the perceived color.
Like cyan.
Here, this is pretty faithful to what your eyeball would see. 19.
Oh, it's green.
It's wicked green. Okay? It's wicked green. So what does that mean? Does it mean the sun is green?
Well, it's definitely got a lot of green.
It's pumping out more green than any other color.
That is for sure. We're also, but I mean, could that just be the average? Why does it appear white?
Average, it's the peak. You can see it, Wyatt, right here. If you look at the spectrum of the sun in slide 53, function F5 53, notice, Wyatt, that the sun, just like we calculated a second ago, let's get the right color here. The sun's peak is right above 500 nanometers. So it's green, but the sun is not actually green. What color is the sun?
White.
That's right. And the sun is white from space. So the answer to the third question has two answers. If we ask, why is the sun white? It's white from space because why? Why is the sun white from space and not green? While you're thinking about that,
Because it's a black body.
that's right. Let's look at a picture of the sun from the ISS. When you actually look at a photograph of the sun from outer space, it's the whitest, purest white that you could ever imagine seeing. And Christopher said it right. It's because it's a black body. It's not just containing only green, but it's mixing together all the different colors of the EM spectrum so that it comes out as very uniformly white because it's a black body. And a black body that gives off all wavelengths of light. Why is the sun yellow?
Ooh, I know this one. Because the chemical composition of our atmosphere causes the shorter wavelengths of light to scatter before it reaches us.
Right. So all of the white light is filtering through the atmosphere, but the blue wavelengths scatter side to side. This is also related to the question of why the sky is blue. Oh, and Wyatt, green minus blue equals?
Green minus blue equals yellow.
All right, it's not quite that simple, but it's kind of that simple. So yellow, because the atmosphere scatters blue wavelengths. Of light. So I'm impressed, Wyatt, that you knew about that. That's pretty cool. They call it, Wyatt, they call it Rayleigh scattering.
It's one of those things where like you always asked when you were little, like, why is the sky blue? Or
Right.
like all these different mundane questions. And then you start to realize once you're older that they actually have really complex answers. And that was
Right.
just one of
So
those.
on that note, Wyatt, when you're an astrophysics student and you learn about like optical scattering in your like 600 level class, the joke that the
Yeah.
professors make with the students is when your kid asks you why the sky is blue, you should respond to him by saying, because of Rayleigh scattering. Like what WTF is Rayleigh
Yeah,
scattering? It's wicked complex. It has like a 1 over lambda to the 4th dependency. I don't even want to talk to you about Rayleigh scattering.
when my kid asks me why the sky is blue, I'm gonna pull out the whiteboard and everything and start going
exactly.
into it.
They're like,
Like, all right,
that's when they say TLDR, you know?
yeah, right?
Okay. Can I erase, friends? All
One
right.
sec.
Oh, sure. Okay, I'll erase now then. Okay. Last problem. Chapter 14, number 61. This is called solar mass loss or something. Wait, Austin, do you want to read this for me?
I'll read it.
Thank you.
Okay, hold on. I need to pull it up though. Okay, solar mass loss. Estimate how much mass the sun loses through fusion reactions during its 10 billion year life. You can simplify the problem by assuming the sun's energy output remains constant. Compare the amount of mass lost with Earth's mass.
All right, I found this problem so terrifying as a student because they really didn't give you any givens. They just said, figure out how much mass the sun loses over its 10 billion year life. And this can be a challenge for new students because you don't know what kind of things you can assume. Well, just like we did in one of the earlier problems, we can assume that the sun is pumping out constant energy in the form of light. And we know that the luminosity is the parameter that tells us how much energy the sun is losing. The sun is constantly pumping out 4 times 10 to the 26 watts. And as we've already discussed in today's office hours, that's the same thing as 4 times 10 to the 26 joules per second. That's the amount of energy that the sun is pumping out into space. Where is that energy coming from? It's coming from nuclear fusion in the core, which I'll teach you about next Tuesday. Now, I want to make an argument that you might not have thought about before. And the argument goes like this. If the sun is producing 4 times 10 to the 26 joules per second at the surface of the star, that must mean by energy conservation that the sun is destroying or using up 4 times 10 to the 26 joules per second at the core of the star. And try to think of the two weirdnesses that would come about if this were not true. If the sun's core produced less than 4 times 10 to the 26 joules per second, then somehow you'd have to get more energy somewhere along your journey through the star. But that doesn't make any sense because only the core is hot enough for fusion. On the other hand, if the sun was producing more than 4 times 10 to the 26 joules per second, then energy would be lost throughout the star. So that doesn't make sense. So we're going to also use the mass of the sun as well, 2 times 10 to the 30 kilograms. We know that in the core of the sun, energy is being produced through fusion. And fusion works according to Einstein's famous equation, E equals mc squared. Mass is destroyed and it's converted into energy, okay? Let's calculate the mass lost in 1 second at the core of the sun. So in the core, the sun converts this much mass in 1 second. So we're going to solve for the mass lost. We're going to do E over c squared. How much energy are we losing in 1 second, students? Shoot, is anyone still with me here?
4 times 10 to the 26 joules.
Thank you. And we'll divide it by the speed of light squared. Go ahead and punch that up. Not shy. I'm not shy. The sooner we finish this problem set, the sooner I can get back to shredding on my guitar.
4.4 billion.
That's right. And what are the units, Christopher? This might be tough. Christopher, remember that a joule is a kilogram meter squared per second squared. No, too much. Kilogram
Very.
meter, sorry?
Very much.
Anyone?
Kilograms?
Yeah, it's a mass.
Oh.
And that's in 1 second. Okay, I kind of need to erase up near the top. I'm going to erase all the middle part, okay? Okay, so what should I do next? Remember, I'm trying to find out how much mass it loses, not in 1 second, but the amount of mass in 10 billion years. So can anyone walk me home here?
Would you convert
Go ahead.
that? So I think you'd want to.
Go ahead, Christopher. I think I know what you're about to say.
Would you want to convert the second into like years and then billions of years?
Yeah, you want to know another approach that we could use, Christopher? We can just awkwardly multiply it by the 10 billion years. And I know that doesn't cancel, but then we can put the unit conversion right in there. Does that make sense? So we'll multiply by the 10 billion years, but then we'll just put in the conversion. So it's kind of like we converted the 10 billion years into seconds and then we multiplied. I think Christopher was going to suggest doing kilograms per year instead, but this is just as fast, so why not? Do you guys remember how many seconds are in a year? That's your bonus conversion factor.
31,000 or 31,536,000 seconds.
Pi times 10 to the 7 seconds per year, where pi is actually 3.15 this time. Okay. Go ahead and punch that up, guys, and tell me how many kilograms we've lost.
(1.4 times 10 to the 27).
Which is pretty close to the mass of the planet Jupiter. So the sun will destroy a Jupiter's worth of hydrogen in its lifetime. If we want to compare to Earth, the mass 1.4 times 10 to the 27 kilograms over 6 times 10 to the 24 kilograms. How many times greater than Earth is that?
Is it 3,000?
I think it's a little less than that, right? I think it's in the hundreds.
Okay.
I got 233.
(230 Earths worth of matter. I don't want to say destroyed because it's not really destroyed. It's converted into light. And that, my friends, concludes homework number 6. Not a bad day's work. Okay. I'm going to stop the recording there for the benefit of the nighttime students.